Hello everyone. So today we will be looking at this Leetcode problem 1498, number of subsequences that satisfy the given sum condition. So the problem statement says that you are given an array of integer nums and an integer target. Okay, so here if you will see, you are given an array 3, 5, 6, 7 and you're given a target equal to 9. Now you have to return the number of non-empty subsequences of nums such that the sum of minimum and maximum element on it is less than or equal to target. Since the answer may be too large, return modulo 10 raised to 9 plus 7. Let's understand what they are trying to say. So one important keyword here is subsequence. We have to return the number of non-empty subsequence. Subsequence can be like 3, 6, 3, 5, 3, 3, 7. Okay, it should not be necessarily continuous. Okay, so 3, 5, 3, 5, 6, 3, 6. These are all subsequences of nums. Okay. So what we have to do is, let us suppose we have this one subsequence 3, 5, 6. So what is the minimum element in this? The minimum element is 3. And what is the maximum element? The maximum element is 6. So what is the sum of both of these? 3 plus 6 is 9. Okay. And what is the target? Target is 9. So their sum should be less than equal to 9. So 3 plus 6 should be less than equal to 9. And if this is the case, then we will say yes, it follows the criteria and we will include it in the count. So we have to find these subsequences whose sum of minimum and maximum is less than equal to the target. So in the given example, if you see, they have listed down 4 subsequences which follow this criteria. And in this, if you see, this is a single element, so the mean and max will be 3. So 3 plus 3 is less than equal to 9. Similarly, 3 plus 5 is less than equal to 9. Similarly, over here, 3 plus 6 is less than equal to 9. 3 is minimum, 6 is maximum. That's why 3 plus 6. Over here also, 3 plus 6 is less than equal to 9. And why we have not taken full 3, 5, 6, 7? Because the minimum is 3, maximum is 7. 7 plus 3 is 10, but the target is 9. So 10 is greater than 9, which doesn't satisfy this criteria. Okay. So the first thing which should come to your mind, or which comes to our mind when we read this question, is that it is a subsequence, which means the order doesn't matter, and we have to find the minimum and maximum. In order to find the minimum and maximum, one thing which can come to our mind is that let's first sort this array, since the order doesn't matter, right? So we need not track where this 5 has gone after sorting. Okay, so first thing which can come to our mind is let's sort this array and then we will try to see how to solve the problem. Okay, so the first step over here will be to sort the array, and after that, after sorting, like this is already sorted in our case, but it need not be sorted. So 3, 5, 6, 7. After this, what we will do is we will pick the first element. Okay, after picking the first element, so we have to find the rightmost index. We have to find the rightmost index such that whatever the number present at that rightmost index plus this number present at the ith index, their sum should be less than equal to 9. Correct? Let us suppose in this case, if we start with I equal to 0, which is 3, okay, and we have to find the rightmost index. Rightmost index will be 6. Okay, 6 plus 3 is less than equal to 9. Okay, why we have not taken 5? Because there is still one element present on its right, which is giving the sum less than equal to the target. That's why 6. And why we have not taken 7? Because it is greater than 9. So we have found that for 3, the rightmost index is 6. That means whatever elements which are present on the right of 6, and like 3, 5, 3, if there would have been some another element 4, okay, all those will satisfy the criteria. Like those subsequences will definitely satisfy the criteria. So that means in the final answer, like in 3 to 6, we can either include 5 or we cannot include 5. Similarly, we can include 6 in the final answer or we cannot include 6. Okay, so for every element there is 2 choices. We can include it or exclude it. For 6 we can include it or exclude it. So 2 into 2, okay, which means 4. There are total 4 subsequences. Okay, so in this case 4 is the answer. So if you will, and similarly what we will do is now we will go I equal to 1. For 5 we have to find the rightmost index whose target equal to 9. Okay, so 5 plus 6 is 11. No, 5 plus 7 will obviously be greater than like target 9. So 5 plus itself 5 is also greater than target. So that means we will not be able to find any element beyond this, so we will break the loop. Okay, so our answer will be 4. So the steps will be, we have to sort the array for each index I from 0 to n minus 1. First we look for 3, find the rightmost index j such that nums of I plus nums of j is less than equal to target, and all elements between I and j, between 3 and 6 over here, can be used to form subsequence. So the number of such subsequence will be 2 raised to power j minus I. Like if it is 2, if it is like 0, 2 raised to power 2 minus 0, which is 2 raised to power 2, which is equal to 4. Okay, so why 2 raised to power j minus I? I have already told you, either we can include it or we can exclude it, which means we fix nums I as the smallest, okay, which is 3 in this case, and the remaining j minus I elements, which is 5 and 6, can be either included or not included. So there will be total how many combinations? 2 raised to power j minus I combinations. Okay, so what is the time complexity for this approach? Time complexity will be, since we are doing sorting, right, for that it will be n log n, and for every element I, we are doing we have to find the rightmost index, okay, which is less than equal to this, like the sum is less than equal to the 9. So for that we have to apply the binary search. So binary search complexity is log n, we have to do it for every element n log n. So n log n plus n log n, which is total n log n time complexity. So in this approach you saw that we took total of n log n. We will see how we can optimize it. Like we cannot optimize the overall complexity because sorting will definitely be part of it. But we can optimize this binary search. Okay. So first of all, let's look into the code. So first of all, here on the 18th line, if you will see, we have sorted. Okay, we have sorted it. And after sorting, what we are doing is, we are taking like I equal to 0 as start. Okay. And here we are checking like what is the number which we need to find. So target minus nums of I. We have to find the number which is less than equal to max allowed. Okay, we have to find this number. So if the max allowed is less than nums I, then it's not possible, then continue. But then we have to find it, so we are using binary search over here. This is standard binary search algorithm where we find the mid and we check if the mid is less than equal to max allowed. If it is less, then we increment the left, that is we have to go to the right, otherwise we will go to the left. Okay, and we are also storing the index over here. Okay, so if the index is not equal to -1, not equal to -1 means we have found the element. Okay, if we have found the element, what we will do is, we will say valid index minus I. If you will see over here, what we were doing is j minus I, right? J is where we have found the element. So valid index minus I, 2 raised to power that. So this is the function which we have written to calculate 2 raised to power n, a raised to power b basically. Okay, so since we have to, like if you will see the question, they are saying we have to return modulo 10 raised to power 9 plus 7. So that's why I have included percentage mod over here. Okay, here also percentage mod. So answer we will keep on, like here you can see, we will keep on incrementing for each I. Okay, so then finally we will return the answer. Now you see this, this binary search could have been optimized if we use 2-pointer approach. Okay, this could have been easily solved using order of n instead of order of n log n. And also you are saying that we are always calculating 2 raised to power 2, 2 raised to power 3, 2 raised to power 4 again and again. Whenever 2 raised to power 4 call goes, it goes over here, recalculate everything and then returns it. So this also we can pre-compute it. Okay, we can pre-compute till a certain number, and that will be useful for us. So let's see how to apply these optimizations. So in the 2-pointer approach, what we have to do is, sorting will be done. Okay, we have to pre-compute the power of 2. Okay, after pre-computing, what we will do is, we will use a 2-pointer approach. Our first pointer will start from left, the other pointer will start from the right. Okay, so while the left pointer doesn't reach, like both don't merge together, what we will check? We will check that the number which is present on the left plus the number which is present on the right, if it is less than equal to target, we will check the number of subsequences which can be formed. Okay, this is 2 raised to power right minus left. Otherwise, since it is too big, okay, so and because the number on the right, okay, is too big, so we will do decrease of right minus 1. Otherwise, what we will do is, we will keep on incrementing the left. Again, why this works? You know why it works. Okay, I have already explained you previously why 2 raised to power j minus I works. So what is the benefit? Is faster than binary search because it is taking just order of n. The 2-pointer approach takes order of n. and we are using pre-computed powers. So sorting order of n log n, two pointer approach order of n, then the total complexity will be order of n log n. Okay. So let's see the code, very short code. What we have to do over here is we are pre-computing power of 2. Okay, we are storing it like a DP, and then we are sorting it. After sorting, what we are doing is we are using a 2-pointer approach over here, where left is less than equal to right. We are checking that it should be less than equal to target, then check what's the count, okay, of the subsequence between this left and right by inclusion and exclusion principle. Okay, after that plus plus left. Otherwise, if the number is like, if it is not matching that, like it is greater than target, then we have to reduce the maximum element. And then finally, we will return the result. So this is a total summary which we read for binary search. What we were doing, we were not pre-compute, like we could have pre-computed here also, okay, the optimization. But the problem is the binary search itself takes order of n log n. And in the 2-pointer approach, what we saw, the 2-pointer approach, it takes order of n, okay. So 2-pointer approach is more efficient in this case as compared to the binary search. I hope this question is clear to you. Thank you so much.